Okay, lecture 22. Let's just jump right into the recap. Last time, we started getting into interferences. Interferences occur when something other than a change in analyte concentration changes a sample's signal. We have so far covered two of the three major types that we encounter in spectroscopy, not including the temperature effects that we discussed in AES. So the two that we did cover so far were ionization and spectral interference. Ionization occurs when a high-temperature collision has so much energy that instead of exciting an electron, it completely ejects it from the atom, causing that atom to become an ion. And that ion has new energy levels, which means that it is no longer capable of absorbing or emitting the wavelength that the atom absorbs or emits. This causes the signal to decrease because these ions are effectively invisible. So how do we fix that? Well, we add an ionization suppressor in excess. An ionization suppressor is a group 1 metal. Group 1 metals lose their electrons relatively easily compared to other elements. And so we can potentially release so many electrons into the environment that even if an ion of our analyte were to form, it could very quickly find another electron and reform the atom, thus absorbing and emitting the proper wavelength. Spectral interference occurs when another chemical in the sample happens to absorb a wavelength of light that is close enough to the analyte's wavelength that we're studying that the two lights overlap, and thus there's an addition to the signal from this other chemical. And so the effect is that the signal is going to increase relative to if this other chemical had never been in the sample. The simple fix to this is to just pick a different wavelength to study. We've seen in the past that all elements wind up absorbing or emitting different wavelengths of light corresponding to different transitions possible in the atom. Among those different options, there's bound to be one that is unique for the analyte that you're studying. Now, the issue with these interferences arises when some of the solutions in your analysis exhibit the interferences and some of the solutions do not. Because if you remember in CHEM, to learn about an unknown, we must always reference a known. And so we can't have discrepancies between the two solutions. So, to judge if these interferences are actually going to present a problem, we should always start by just drawing a calibration curve that represents everything going properly, and then ask ourselves three questions. 1.
Which sample experiences the interference? 2. How does the interference change the measured signal? And 3. What is the consequence on the calculated unknown concentration?
And we saw examples of how these questions are used when we covered the first two interferences, and we'll see another example momentarily as we get into the last interference. And that interference is called chemical interference. So chemical interference. This is caused by the formation of compounds of low volatility that are not easily atomized. In other words, we form chemicals that do not vaporize in our high temperature environment, and so we don't get gaseous atoms, which means they're not going to absorb or emit the proper light wavelengths. So chemical interference, formation of compounds, of low volatility. And in parentheses, we'll write not easily atomized. Not easily atomized. So for example, using our calcium analysis, what if there was some sulfate present, SO4 2-? Well, sulfate in a sample forms calcium sulfate solid. So sulfate in sample forms CaSO4 solid. And this solid is not easily vaporized, and so any calcium that's precipitated out into CaSO4 will not be detected by our instrument. So let's go a little bit further into this. Imagine we had a calcium sample that was 2 ppm in concentration. Okay? In principle, this is what's supposed to happen. In flame, we convert all of that into calcium atoms in the gas phase, and we would have 2 ppm. Okay? But what if some SO4 2- is present? If SO4 2- present, then let's say that 1.8 of those 2 ppm are still unreacted. But the other 0.2 ppm bonds to that sulfate and creates this low volatility solid. Well, between the two chemicals, we still have a total of 2 ppm calcium. However, not all of that calcium will atomize in our flame. Once we put this into the atomic spectrophotometer, what we're going to get is 1.8 ppm of calcium gas, which we will be able to analyze, but the rest of the calcium remains in this solid precipitate, which we won't be analyzing. So, not atomized. Thus, not measured. Signal goes down. Signal lowered. Our sample might be 2 ppm calcium, but we're only measuring 1.8 of those ppms. So let's tie this in with our calcium analysis example. Let's say that the third standard was contaminated with sulfate. What will be the effect on the calculated calcium unknown concentration? We'll assume that all solutions have a large CS concentration. This is a group 1 metal, so it's an ionization suppressor. And the large concentration is meant to imply that all ionization will be suppressed. Furthermore, there is no spectral interference. Now you can only assume that because I'm telling you this. If I didn't tell you, you might have to read the problem more carefully. But in this case, the only potential interference is chemical, which will happen when that sulfate mixes in with the calcium of standard 3 for the reasons we just covered. And so, one more time, we'll go through this process. We start by just drawing the analysis if everything goes correctly, and then we ask our 3 questions. 1. What experiences the interference? In this case, it's only standard 3. 2. How does that affect the signal? Well, it brings that particular signal down. But all it takes is one standard to go wrong, and that's going to drive the entire curve down with it. And so let's say our curve winds up here, falsely low. Our unknown measures correctly, there's no chemical interference, so we plug that reading in and we get a falsely high reading. So all 3 of our interference examples that I've given in this lecture have involved the final answer being falsely high, but that is not a guarantee. If I had instead said that the chemical interference or contamination was in the unknown, then this value would be going low, and it would be plugged into the correct curve, and we get a falsely low reading. If I said that there is contamination in both the unknown and the third standard, we wouldn't be able to predict what would happen because we would know this would go down and we would know the curve goes down, but no indication of which one goes down more, or do they go down by the same amount. Okay, so all these different scenarios can happen, and you just need to be able to evaluate each one, which is why it's important to understand the concepts, the 3 questions that we ask ourselves, and go from there. Now, I will end by quickly saying you how we can fix chemical interference. Fix. Add a chemical that preferentially reacts with the interference. Add chemical that preferentially reacts with interference. For example, if we had strontium in our solution, Sr2+, well, Sr2+ reacts with sulfate to produce SrSO4, solid. And it reacts preferentially. If there's strontium, then it will typically outcompete calcium for bonding with the sulfate. And so strontium winds up taking the sulfate out of solution so that it's not able to react with the calcium and cause the interference. And we don't actually care that we're forming this precipitate because we're not interested in analyzing this part. So hopefully that all makes sense. Now let's add chemical interference to the slide from the recap so that we have a full summary for our reference. In the next video, we'll cover an analysis method that's not based on the calibration curve that allows us to circumvent most of these issues.